Okay, so can you hear me? I can hear myself. So my name is Gidi Navon. I'm a senior principal architect at Marvell Semiconductor. And today I'm going to talk about how we believe we can use open interface to advance artificial intelligence and machine learning in networking, and what we believe OCP, the role of OCP can do in this area. A few words about Marvell. Marvell is a global fabless semiconductor company with over 6,000 employees worldwide. We have over $3 billion in revenue. We've been founded 25 years ago, and we have R&D centers around the world. In recent years, we have concentrated on data infrastructure products, and we enhanced our position using several acquisitions: Cavium, Aquentia, Avira, Inphi, and lately Innovium, that brought the Terralinx switch, which is a high-performance, low-latency, cloud-optimized switch. And a few words about our products. On the compute side, we have our Octeon DPUs that can be used in smart NICs, in security solutions, in 5G base stations. On the networking side, we have our high-speed interface transceivers, coherent DSPs, copper PHYs, our Prestera and Terralinx Ethernet switches, and we have Ethernet solutions for the automotive market. And on the storage, we have HDD and SDD controllers. We have fiber channels adapters, and we also have a custom ASIC business. So machine learning is being used in a wide range of applications, but not so much on the network itself. And the question is why? And we believe part of the reason is because when it is used, they're using dedicated, closed, proprietary interfaces that are trying to crunch 100% of the raw data. And we believe that if we define open interface between the network and the AI applications, and if we define what are the important features that needs to move from the network to the AI, we'll be able to create a much more cost-efficient solution. I mean, OCP is all about disaggregating. We've been working several years about disaggregating the hardware from the software. And now we want to try to do similar things between the network and the AI. So a few words about what I'm going to talk today. So first, I'll list a few use cases of what machine learning can do for the network, and then discuss some integration options of the AI into the network and what the network can provide the AI, and then about the role of the OCP in the SAI working groups, in the Sonic working groups. And last, I will show a real-life use case, a demo of how we can detect anomalies in high-speed networks. So let's list a few use cases for machine learning. And the first use case is called application classification. It's the ability to classify flows into their application just by looking at their traffic patterns. So it can work also on encrypted flows. Once you classify this application, you can assign class of service to the packet. You can drop flows which are not allowed for applications that are not allowed. And those type of algorithms usually use supervised learning, that you need to tag each one of the applications that you want to later classify. A second group of use cases is trying to detect anomalies in the network. If there's an anomaly in the network, maybe something is wrong. And they can be a malicious flow that is penetrating our network with traffic patterns that is not familiar with in the normal traffic. It can be a flow from a new source that is sending exceptionally high traffic and maybe trying to create a denial of service attack. It can be the devices that have faults, and because of faults, maybe they're stopping to send periodic reports. A misconfiguration, of course, can cause anomaly behavior. It can also be content theft, maybe a surveillance camera that is sending traffic to destinations that it is not meant to send. Such algorithm can also use supervised learning, but then you need to train for each and every possible anomaly in the network, so what people usually do is do unsupervised learning, which means you train the model on the normal traffic, and then basically everything else is considered an anomaly. A third group of use cases is related to our desire to automate the network and run big, complex, dynamic networks using the same small IT staff. And the machine learning can help. It can help analyze huge log files and many events that it can try to correlate and try to find a root cause that is causing many problems. It can help in configuring and designing networks, for example, deciding the location of a Wi-Fi access point. Now, those three first sub-use cases are very important and very important to the IT department, but they don't need to track the traffic itself. They're using logs, they're using alarms, but they don't need to track the traffic. But machine learning can also be used for example, traffic prediction by looking at the traffic patterns. And it can also try to look at the traffic pattern and based on that, to identify what device is connected to the network. Is it a sensor? Is it a server? And those last two sub-use cases do need to look at the traffic patterns continuously. So they need statistics which are closer to the previous anomaly detection use case. So after we talked a little bit about several of the use cases and what the machine learning can bring to the network, let's discuss about how to integrate it. So one option is to have a big centralized AI engine, maybe even in the cloud. Alternatively, you can distribute the AI to each and every networking device. Now, centralizing the AI, of course, has many benefits. You can reuse resources much more efficiently. But does it mean that you need to duplicate the entire traffic from the network to the AI? It doesn't scale. So, but even if you distribute the AI to every networking device, you still do not want to duplicate the traffic from the fast pipeline to the AI. So the general challenge in AI for networking is how to really monitor big networks with very high packets per second. And the way we think this should be done is by embedding smart feature extractors in the fast pipeline to provide the AI engine a condensed important features that the network can provide, not every packet, but every group of packets. And this is important both in the case that you want the AI to be centralized, but also in the case that you want to make it distributed. So in both cases, you want that the number of events that the AI engine will handle would be much lower than the number of packets per second. And there are multiple strategies and multiple techniques that we can reduce this amount of traffic. If we look at the traffic patterns in campus networks, we can see that 85% of the packets are from large flows of 1,000 packets or more. This is what's usually called elephant flows. But the average flow size is about 78 packets. This is because about 75% of the flows are of very few packets, of 1 to 4 packets. This is what's called the mice flows. So if we examine only the first n packets of the flow, maybe every 4 packets of every new flow, and the average packet size is 78, we reduce the amount of traffic to about 5%. And if we carry only the headers without the payload, it further reduces the amount of data. In addition, if we will be able to define stateful mechanisms that will send different statistics for the very short flows, for example, DNS flows, if we will provide different statistics for them, the number of new flows that the AI engine needs to be aware of will be dramatically reduced, all those very short flows. This technique of sending the first n packets of a flow is good for application classification. But in some cases, you need to continuously monitor the flow for the entire life of the flow. For example, a flow that starts as a benign flow and later becomes malicious or becomes abnormal. So in those cases, we need to define a different maybe mechanism to reduce the data. We can provide a signature of the traffic pattern. For example, the statistics about the packet size distribution and how does it change over time. And And this will be the way to reduce the number of information sent to the AI. We believe the OCP has an important role in enhancing this area. First, in the switch abstraction interface layer, we need to update the SAI APIs to carry those smart statistics from the network to the AI application. This can be done by enhancing existing tables like the TAM, the telemetry and monitoring tables, but it can also be using a new sets of APIs, maybe the stateful API that was discussed earlier today. We also need to define the actual data formats to make them condensed and compressed. And we also need to define the triggering mechanism. Should it be periodic or should it be event-based? Now, apart from the SAI working group, we also can work on the application layer. We should allow companies to contribute applications, application classification, anomaly detection algorithm, to contribute those and place them in a Docker container. We can also try and standardize the interface between the AI application and the AI hardware accelerators. OCP can also work in becoming a place as a repository of AI models. We can have a model of what is a device behavior. And this will allow us both to do device identification. This port is connected to a sensor versus a server, but also can be the model for the normal behavior device, and then this will be used for anomaly detection. For the flow classification use cases, it can be a repository of signatures of malicious flows that are known to the industry. And for the automated network use cases, we can decide on the structure of the logs and the events, so companies specializing in crunching those logs will be able to receive logs from different vendors. Okay, now I want to discuss a real-life use case that we have done and shown that those traffic reduction techniques can actually work in real life and still able to detect anomalies. So if you look at the classical framework of anomaly detection, you have a network sending packets to some sort of a AI server that needs to run an anomaly detection algorithm and place the results in a log. Now, if we look at what the AI server is actually doing, it first needs to capture the packet. It needs to parse the packet headers, to take the packet size, the packet arrival time. Then it needs to create some sort of features like statistics like mean, standard deviation on the past history of the flow. This is called damped incremental statistics. And then run the anomaly detection algorithm itself. Now, what we have done in our work, we created a new feature extractor that works on a large group of packets. And we place this in a database. These statistics are, for example, looking at the min size packet, the maximum size packet. The packet size, we have a counter of the packet size per each packet size range, like a histogram. And then we send this smart statistics every second, for example, not every packet. And then we send it to the feature, the damped incremental statistics that needs to be done, and then to the AI machine learning model. And the model that we have chosen has two phases. There's a phase of feature mapper that clusters the features into groups and sends each group to a small neural network, something called autoencoders, but other models are possible. We chose one machine learning model. And to explain a little bit about this model, it's a model, this autoencoders is a model that is meant to create a small representation of a big data set. And it is a concept taken from the image processing, from image reduction, dimensionality reduction. What it does is you take an image. In the encode phase, they reduce the number of elements of the image. And in the decode phase, you try to reconstruct the image. And using iterations, you try to make that the reconstructed image will be as close as possible to the original image and minimize the error, the mean square error between the output and the input. Now, this same concept is now being taken for networking and anomaly detection. Instead of an image, you train the model on the behavior of a normal traffic or on the smart statistics that we gathered before. And in the encode phase, you basically identify the key characteristics of a normal traffic. And again, you do a decode, and you try to train the model multiple times, multiple iterations. In each such iteration, you update the coefficients of the neural network. But later, when abnormal traffic is entering the network, but the network itself is trained for normal traffic, the received output layer is very different than the incoming, the input layer. So this mechanism is basically amplifying the difference between normal and anomaly networks. And it's thus much easier to detect. So if we look at this enhanced framework, after we added this smart statistics and the reduced number of events, we can see that packet capture and packet parsing and flow classification are all done in any networking device. Also, the smart statistics can be done in modern programmable pipelines. And all those four first steps needs to happen per packet. So it makes much more sense to embed them in the fast pipeline of a switch. But later, we can stream the reduced number of events to the CPU to do the damped incremental statistics and to the AI to do the machine learning itself. But this time on a reduced number of events. So the left part is done per packet, but the right part is done on a reduced number of events. Now, and this allows much higher performance. And if we further embed the CPU and the AI engine into the networking device, we distribute this algorithm and achieve much higher performance. And of course, also reduce the load on the network itself. So we tested it in a live network in our lab. We took the example of sensors. We tried to see if we can identify abnormal behavior of a sensor. During the training phase, we trained the model for a couple of minutes about the normal behavior. And later in the inference phase, we first injected normal traffic to make sure we don't have any misalarms. And then we added anomalies and tried to detect them. The first anomaly, we changed the setup of the camera. We changed the resolution and the video quality. And this can mean somebody has tampered the camera and changed something intentionally or unintentionally. The second type of anomaly, we tried to send traffic to the camera that is not intended, like logging attempts. This is maybe something, again, trying non-authorized attempts that are not part of the normal traffic. And third, we tried to consume more video streams out of the camera, maybe sending it to a client that was not part of the normal traffic. And the results were extremely good. We see here that when we injected normal traffic, all the events were below the threshold, meaning they are defined as normal traffic. But later, when we injected anomalies together with normal traffic, we saw that we are able, that there are those red dots on the top are the anomalies. And then we created normal again with no false alarms, et cetera, et cetera. Now, if you look at this triangle, you see that the number of events per second are quite low, much lower than the number of packets per second. This is because of the smart statistics and the reduced number of events per second. OK, so to summarize, we showed today that several use cases of what machine learning can do for networks and the challenge of machine learning to process high-speed networks and the need to reduce the number of events per second. We showed what the networking device can do, how to reduce this amount of traffic, and then about the role of OLCP in the SAI working group and the Sonic working groups. And lastly, I showed a real-life use case that shows that even though we reduce and create smart statistics on the networking device, we still are able to detect anomalies in high-speed networks. Thank you. I think we have time for some questions. Okay. Thank you very much.